Your understanding of thermodynamics depends heavily on understanding the three following equations. Delta G naught equals delta H naught minus T delta S naught, which equals negative N F E naught cell, which equals negative R T natural log of K. So we're going to start with delta G naught first. Delta G naught represents the maximum amount of energy found from the usable work of the system. In other words, delta G naught represents the thermodynamic favorability of the reaction. So if delta G naught is negative, the reaction is thermodynamically favorable. In other words, the reaction is thermodynamically likely to happen. In contrast, if delta G naught is positive, the reaction is thermodynamically unfavorable. So the reaction is thermodynamically unlikely to happen because you have to put in energy to get that reaction to go. So note that this thermodynamic quantity does not tell you about the rate of the reaction. So a reaction could be under what is known as kinetic control. Kinetic control basically means the reaction has such a high activation energy that it's going too slow to be appreciable. Another thing you can do with delta G is you note that it's a state function, so you can do something known as coupling. So I'm going to write that down first and explain it. So delta G if you don't know what a state function is, that just means you only care about the starting and ending state. It's not pathway dependent. And that's important because that means you can add delta G naughts. If you're familiar with Hess's law, it's the same sort of idea. So we can take a reaction that's thermodynamically unfavorable, which is positive delta G, and depending on the magnitude of the negative term, we can make that reaction thermodynamically favorable if that negative is greater than the positive. So there's your quick summary of delta G naught. Let's move on to delta H naught. This is going to be mostly a summary of thermochemistry, so if you feel pretty good on that, you can go to this part right here, delta S naught. As a quick reminder, your delta H naught is measured as heat at a constant pressure. There's three main ways to find that. You can use Q equals ms delta T. You can use Hess's law, and you can estimate with bond enthalpies. So all these methods have their own complications that CollegeBoard is going to add on to them. So this, right, your calorimetry, there's probably going to be error analysis. There's probably going to be at least one of them that shows, calorimetry is a really easy spot to put it. So the question is, if the calorimeter isn't insulated, how will that change your Q? If you use more mass, how will it change your Q? If you use less mass, how will that change your Q? So that's the kind of questions they might ask. With Hess's law, one thing to remember is that you're probably going to ask about mole reaction and molar enthalpy. If you're unfamiliar with mole reaction, for the generic reaction, X moles of A goes to Y moles of B. 1 mole, or X moles of A, of A, is 1 mole reaction. And the same goes with Y moles of B is 1 mole of reaction. So that's essentially a way of getting the molar enthalpy with delta H naught. Finally, with bond enthalpies, the one kind of thing to take note of here is I have 2 moles, let's say, of water. Then that is 2 times 2, because that's the 2 OH bonds there. That's something a lot of people forget, times then finally your OH bond. Okay, so there's your quick summary of calorimetry. Now we're going to move on to the new part, which is entropy. So your entropy, your standard change in entropy is going to equal your delta S naught. And entropy is really relates to microstates. So your microstates are essentially the number of possible configurations there are of the atom, how much dispersal there is. So when you say dispersal, right, that kind of brings to mind phases. So your solid is going to have less entropy than your liquid, is going to have less entropy than your gas, because the gas is more dispersed. There's more places those gas particles could be. And the same thing with electrons, right? If I have an atom with more electrons, that's going to have greater entropy than one with fewer electrons. Furthermore, if I have more moles of gaseous products than moles of gaseous reactants, that's also going to increase the entropy. And sometimes it doesn't even necessarily have to be a gas. So, entropy, right? One other thing, kind of caveat, you'll notice we haven't mentioned aqueous. So, everyone's favorite thing about AP chemistry is all the exceptions, right? So, aqueous could be positive or negative delta S naught. And that's because of the dissolution process. When you think physically of dissolution, right, I'll add that in, dissolution, you'll remember, hopefully, that let's say I have an anion here. Let's say I am solvating it with water, which is happening in the dissolution process. You pull the water apart, pull the salt apart, and then form these ion dipole forces. Well, this orders the water. This makes the water have less microstates. And the ion really has greater microstates because they're further apart, they're more dispersed. So really, it's a question of which is going to win, the increased microstates of the ions or the decreased microstates of the water. And they don't expect you to know or memorize those. It's just important to know to not be freaked out if you have an aqueous dissolution process in which the entropy is negative, because those water molecules or perhaps those ions are more ordered because of the solvation process. So now we're familiar about getting delta S naught and how we get there and predicting it. So now we have to go back to delta G naught and understand, okay, if I have my enthalpy, and I'll draw it down here, if I have delta G naught equals delta H naught minus T delta S naught, if we have a negative delta H naught and positive delta S naught, remember that this negative sign here, you're subtracting that. So negative minus positive is always going to be a negative. And same thing with when you flip these signs, a positive minus a negative, that's going to make this always positive, because a positive minus a negative is a positive plus a positive, always going to be positive. Really, it's unsure when you get to the same sign. So if I have an endothermic process that decreases in entropy, then this is when the magnitude of the temperature matters. Same thing if you reverse that, you can't say because the magnitude of the temperature matters. So let's say I have an endothermic process that, sorry, I wrote the same sign here. I don't know why I did that. If I have an endothermic process that increases entropy, well, it's a positive minus a positive. If your T has a great enough magnitude, then your delta G is going to be negative, so the process is thermodynamically favorable. But if I have a positive minus a small temperature at a low temperature, then that reaction is not going to happen because that delta G naught is not going to be negative. Moving forward, we have negative NFE naught cell. So I can't teach you all of electrochem in this lecture on thermodynamics, but I'll try to give a quick summary of what's going on here, and hopefully you can revisit this after learning electrochem if you haven't already, and realize it makes a lot of sense. So your N here is the moles of electrons transferred. And you just have to make sure this is from the balanced reaction, okay? For example, if one of my half reactions has two electrons transferred and the other one has 3, then your N would be 6 here because 6 electrons in the balanced reaction are transferred. Your F, that's a constant, always 96,485 coulombs per mole of electron. And then your E naught cell, this is what a lot of the chapter on electrochem focuses on. Your E naught cell is calculated from the half cell potentials of your anode and your cathode. Really, the important thing here is to recognize that because this term right here is negative, if your E naught cell is positive, that means it's thermodynamically favorable. Because a positive E naught cell makes a negative delta G because of that negative sign in front. That's also a galvanic or voltaic cell. Okay, if it's negative on the other hand, it's thermodynamically unfavorable. And that makes it electrolytic. So what you can tell about the cells from these names is that if it's galvanic, you can measure the volts with a voltmeter. But if it's electrolytic, you need to provide the power in order to make that process spontaneous. Because originally, because the delta G naught is positive, it's not going to happen without excess energy being put in. So, that's a quick summary of that. Oh, sorry, one other thing I forgot is that this is not an AP Chem topic, but if you do USNCO or if your teacher just might be rigorous, maybe your teacher wants to teach you at Gen Chem at USNCO level, E naught cell is an intensive property. Intensive. So what does that mean? That's in contrast to delta G being a state function. It's extensive, right? What this means is that you can't add them with Hess's law. So if I have two different reactions, you cannot add it up with Hess's law. You have to convert to delta G so that you can couple it, right? Notice how this all ties together. You convert to delta G so you can couple it and then convert back to E naught cell. So that's not an AP topic. You don't need to worry about that. But if you want to get better at chemistry, I would recommend looking at USNCO 2024, number 42. So that's really the majority of your electrochem. Now you just need to learn how to calculate that, which I won't do here. And now equilibrium, kind of same thing. We're gonna ignore all the K stuff and the equilibrium concepts themselves and just do some quick thermodynamic reminders. So remember, this is 8.314 joules per molk, right? We don't use 0.08206 because that's the used for like the ideal gas law and stuff, but not for thermodynamics. We need to work in joules. And units are important for jumping back over here with your delta H naughts and your delta S naughts. Those usually aren't in the same units, so make sure you're always paying attention to units in thermo. Your temperature, of course, I'm going to go back to units. Make sure it's in kelvins, so that Kelvin, those can cancel. And we're going to skip the natural log of K. Hopefully you know to do equilibrium. And we're going to go ahead and connect the equilibrium part to the electrochem part with the Nernst equation. So E cell equals E naught cell minus RTnF. Natural log of Q. Okay, so in AP, you won't have to do calculations with this, but you will have to understand it conceptually. So this is non-standard. So when can you have a non-standard condition? So that might be when your temperature isn't 25 degrees Celsius. It might be when your when you aren't at K, when you're at Q. So same thing with error analysis that I mentioned back here. It's helpful to think about this in like the equation form. So your Q, if you remember, for like your generic reaction, you got, oh my god, that's horrible, A B over C to the C times the concentration of D to the D for your Q. And so let's say the product concentration increases. You can think, okay, this whole term is going to increase, and it's because, remember, this negative sign is going to make E naught cell decrease. Or, sorry, E cell. Hold on, I'll write that more clearly. So E cell is going to be less than E naught cell. Because if you think about it from like a Le Chatelier's principle, that reaction is going to go backwards. Now, if you increase the products, that reaction is going to go forwards. They're going to be reacted away. If you think about it from mathematical sense, this term is going to be smaller. So I'm not going to write the mathematics out here because it's a bit more varied than the first time. But your E naught cell is going to be either pretty close to E cell, or it's going to be greater than E cell. And the same logic applies with temperature, right? You can see how temperature increase and decrease changes that term. And I mean, it also makes sense if you wanted to apply K here, right? If I am at standard state and all of these A, B, C, D are all 1, while natural log of 1 is 0, so E cell would equal E naught cell at standard state, which makes sense. So this really is your summary overall of all of Thermochem, all of thermodynamics. I hope it all made sense. Thermodynamics, it really brings in a bunch of different concepts from the whole year. It's very useful to look through it and like look through your old notes as well in case you need some refreshers. Thank you for listening. Hope that helped.